Okay, so that was a very nice question from the audience, namely, well, let's just look at the case where we have, 4 variables, and we have this very nice graphical model here. Let me just draw it in slightly better magnification. So we basically have, x1, x2, x3, and x4. And these are unobserved, latent. But instead of that, we actually do observe, a z1, z2, z3, and z4. Can't really pull anything out of thin air right now in terms of a very practical example of that very specific model. If anybody can, please let me know. But what I'm interested in is to infer the probability of x2 given everything else. So let's just write it out without all the products and everything. So we have basically P of x1. We have P of x2 given x1 times P of x3 given x2 times P of x4 given x2 times, and now I'm just being a little bit lazy here, product I going from 1 to 4, P of zi given xi. And the variable that I'm after is x2. This guy occurs here, 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 and it occurs exactly for I equals 2. Basically occurs here in one case. Okay. Now, in order to achieve this goal of getting a handle on P of x2 given everything else, I need to integrate, and of course I need to integrate out over the unobserved variables, because I can't really condition on them, I don't know what their value is. The only way to really achieve this is I need to sum over x1, x4, and x3. So fortunately, as it turns out, the x1 terms don't depend on anything but x2. The x4 terms don't depend on anything but x2. The x3 terms don't depend on anything but x2. That's like the message from here, there, and there. Right. So pulling out the x1 terms, we have P of x1 times P of x2 given x1 times P of z1 given x1. So I can perform a summation over this, and this is going to be some function, m going from 1 up to 2 of x2. I can do the same thing for x3 and x4, and I'm just way too lazy to do that right now, but it works out in exactly the same way. So we'll get a message 3 to 2 and a message 4 to 2. Now the only term that's left over is then, we'll have the message 3 to 2 and a message 4 to 2. And now what I also have left over is P of z2 given x2. Okay. So now the only thing that's left is to actually make sure this is a proper probability distribution. And right now it's not normalized yet. So what I do is, this expression now is some function, let's call it psi x2. And I know that this is proportional to P of x2 given the rest. So how do we figure out then what the probability is? I just take this. So therefore, it's this divided by the sum of psi next to. That's it. So this is the simplest example of message passing, because we didn't really have to generate a lot of messages. They were essentially already there. Now, if I wanted to do inference maybe on x4, well, I'd have to sum this term out, I'd have to sum this term out, and then I get something that only will affect x4. The cool thing is that I can actually get all the marginal probabilities here, x1, x2, x3, x4, essentially at the same cost as what it costs me to get one of them. Actually, it's twice the cost, but it's the same order of magnitude. Why? Because in order to get my hands on x2, I need to compute this guy here, and this guy. Now, if I wanted to compute, you know, term for x4, well, in this case, I'm already there, right? Already one. This guy I already have. So the only thing that I need is this one. In order to compute x3, well, also very little extra work, because I already have this, and I just have to get this message. And to get x1, well, okay, I have to get this guy. Everything else is already there. So what you see is basically you only need to compute a message in both directions once, and that's it. And to get the marginal probabilities, all you do is you take all the incoming messages, multiply them up, multiply them with whatever potential you have that only depends on the variable that you're interested in, nothing else. And that gives you the unnormalized probability. Here's another cool thing that you can do with this. Remember, we normalize in the end. So that means that anyway in the process I can actually go and multiply these terms with, you know, arbitrary numbers. I could, you know, multiply this with 99 and this with 42 and this with 0.0001, and stuff will still work. You sometimes actually need to do this in order to ensure that your functions are properly normalized, that you don't get overflows or underflows. So be careful of this in practice. You will more likely than not actually need this. So that's what we have for trees. What we're going to do now is we're going to do the very same thing for junction trees. Does anybody have questions about the trees? Because I'm going to assume that you know this now when we go from trees to junction trees. Any questions now? Okay. Good. Now's your last time. Going, gone. Right. Junction trees. So I tried hard to find a tree at the junction. Wasn't very successful. So let's just revisit what we had. So this example of 1, 2, 3, and 4. Right. So this was our message passing, right? And what I'm going to do is going to sound initially a bit crazy. I'm going to use. I'm going to write, you know, vertices that, you know, share an edge as pairs, and I'm going to, you know, just line them up. I'm going to draw an edge between them whenever the intersection between those sets is non-empty, and otherwise I'll just leave it. So what we get is all of a sudden this graph here turns into a chain. And nothing really special has happened, so I get, you know, the pair 1, 2, I get the pair 2, 3, I get the pair 2, 4. And what's already interesting is that this green box, which contains the variable in between, is always 2. So the separator set, that's how you call it, between those two sets, so that's basically the intersection between the three adjacent sets, this case is 2. Now, why does it matter? Because it actually turns out that I can write this entire joint probability distribution as something which is expressible in terms of clique potentials, and in some cases you might have some agent potentials as well, but basically those clique potentials. And the messages that we send from one of those cliques to the other one is going to be only in terms of the variables that those cliques have in common. So if you look at our setting here, the messages there were in terms of x2. The messages that go back will also be in terms of x2. So that's the one variable I can get rid of. Like what's there. And this is just a representation of the same situation in terms of graphical models. In terms of cliques. And as we will see, not today, but next week, is that in undirected graphical models, expressing a dependency graph in terms of maximal cliques and so on, so this will give us the Hammersley-Clifford theorem, and we'll probably have a bit of fun with that before we dive right into applications. Okay. Who hasn't seen junction trees yet? Raises their hand. One. Thanks, by the way, for being brave and honest. So, by all means, if you don't know something, raise your hands. If you don't raise your hands, I'm going to assume that you know it. And trust me, it's a lot more embarrassing if you can solve the homework than raising your hands now and saying, I don't know it. Because if you say right now that you don't know it, I can actually explain it back to you again. And I'll explain it until you know it. So don't worry about that. But don't ask me in the homework after 2 or 3 weeks what a Gaussian process is. This is not a good strategy. I mean, I'm happy to explain it to you then when you come to me, but ask earlier. Okay, so here is now a model that looks a lot more messy, right? So what I've drawn here is, a set of 6 random variables, and they depend on interesting ways on each other. Maybe 2 depends on 1. I haven't actually drawn any arrows here. I'm just drawing some dependency graph. Now what I can do is I can actually look at the maximal cliques in this case. And that's the clique 1, 2, the clique 2, 4, 5, the clique 4, 5, 6, and the clique 2, 3, 4. And so I can go and again, draw a tree. So I'm connecting 2 of those cliques whenever they share something in common. In this case here is, the 2 that's in common between this clique and that clique. There's the sets 2 and 4 that's in common between this and that one. And the set 4 and 5 that's in common between those 2 cliques. And now I'm going to play the very same game that we did before. So it's exactly the same procedure as here. Just that all of a sudden now our sets of variables look messier. That's the only real difference. Basically, what I'm going to do is I'm going to express my joint probability distribution in terms of products of functions that depend on, these 2 variables. Then there's going to be some functions that depend on those 3 variables, on these 3, or on those 3. And if I want to sum everything up, let's say I want to sum up everything here. Well, I can't really quite get rid of everything because this next term here depends on the 2's, on the x2's. So the only thing that I can really get rid of here are the xy's. Okay. So I'll get the message going from the left to right that depends on the x2's. Now the message coming from over here, well, I can get rid of the x6, but not of the 4's and 5's. So I will now have, some message which depends on x4 and x5. This guy here. And I'll have another message, which, if I want to generate it, the message from here to there. Basically, how all this mess affects these 3 guys up here, which will depend, of course, on the 2's and the 4's. And this is really all that there is to know about junction trees. So what we did before in terms of trees, we now essentially turned a perfectly good tree-based road system into an American version of that, where you have several highways, several lanes. So that's probably the easiest way to think about junction trees. Question?
Two questions. One is sort of the big picture question, which I get as to junction trees. Is the whole purpose of doing this just because we can run the same some product algorithm on a non-tree structure?
Correct.
Is that the sort of
So the sole purpose of this is for the purpose of this class at least, that we are going to be able to actually integrate out variables and come up with a very mechanical version of, the sum product, or, basically any other semi-ring, and we're going to encounter various semi-rings in a moment. Probably in about an hour they'll come in, where you can essentially review a lot of algorithms like the Viterbi algorithm and so on in that setting. So there are probably 3 landmark papers. One is called the Generalized Distributive Law. The other one talks about factor graphs, and there's a third paper which also has the Generalized Distributive Law in the title. But those 3 papers, essentially in information theory about maybe 8, maybe 10 years ago, really made it fairly explicit how dependencies between random variables, or generally algorithms on semi-rings, can be computed efficiently, and why a lot of very clever algorithms are actually instantiations of the very same thing. So, and what I'm showing you here is, leading you very slowly up to the point where we will see a large class of algorithms satisfying the same rules.
The other question is, I guess your answer is, we can use the same sum product algorithm that works in a tree.
Yes.
The other question was, do you have any slide on getting the actual marginal probability on a specific single row?
Okay, so
because now you have to group up all of them together.
Great. So first of all, the good news is, at the end of doing this procedure, for instance, we could get our hands on, the joint distribution over those guys 2, 3, and 4. So we'll have some function which lets us evaluate for every combination of 2, 3, and 4 what the joint probability distribution is. Now, if I want to get information just about x2, well, the only thing that I can do now is I actually have to integrate out x3 and x4 explicitly, but to get to the point where I have a joint distribution in those 3 variables, this is where I can use dynamic programming. From that point on, it's brute force anyway. But doing the dynamic programming operations, at that point you would have had to perform similar integrals already anyway, or sums. I mean, it'll be integrals in the Gaussian case, or in some other continuous variables, but for the discrete case it might be sums. So basically this is not harder than what you already had to solve for the message passing anyway. Okay, so the big picture is that right now we're doing all those operations for sums and products. We multiply those messages and we sum over them. Later on we will redefine what sum and product means. And we'll get different algorithms. So we'll get, for instance, shortest path algorithms out of that. And the cool thing is, for instance, if you implement a graphical model library in Python, or also in C++, you can just actually define a plus and a times operator. And then you do operator overloading, and instantly you can switch between algorithms by just changing your class. So many years ago, Julian Macaulay actually did, so a student of mine at the time, did this for his, basically undergrad project. That was quite cool, so as his demo he showed how you could easily solve Sudoku, for instance, in this way. So it's conceptually sufficiently simple that you can just, really think of this as, operator overloading, and you replace one by the other. And so there are some very, very bright people here in Berkeley, like Bernd Sturmfels, who study what's called tropical geometry. We'll get to that in a little bit. And essentially that's one specific way how to replace plus and times by another operation. In that case, it's going to be max and plus. Okay. So let's just review what happens in terms of the dependency graph, right? So when we pass a message from 1, 2 to 2, 4, and 5, we basically do this. We take this, move it in here. When we pass a message from 4, 5, 6 to 2, 4, 5, we do this, right? So now we have basically these variables covered, and we can, sum over, in this case, 5 to generate something for 3. You could do this explicitly on paper, but it gets very, very tedious very quickly, which is exactly why you want to use graphs.
So for the click potential retranslation, it seems random. You put the 2, 4, 5 in the middle. Like you can also, like.
No. I'm basically drawing an edge between any maximal clicks that share, that share variables.
1, 2, and 2, 3 4 also share the 2, right?
Yeah. So, which one?
1, 2, and 2, 3 4 is kind of connected through the 2 items, but you didn't draw a direct thing.
Yeah, that's true. Yes. So.
But so you can switch, you can put other things in.
Because I've already, that variable's already shared. Okay. So here's an example of where things can actually go horribly wrong. So let's just, draw the, corresponding Junction tree, and no, this is not a tree. So what can you do about it? I mean, the big culprit here is really that this variable 1 links everything up. So how do we get rid of the 1? Well, I basically make that part of everything. And what that really means is I'm, so first of all you can see the separator set will actually get larger. But what's really happened is I've, triangulated the graph. So I've basically added spurious connections here, which don't really do anything in terms of the functions. But now I have larger clicks, and I get a nice tree. Well, I get a chain actually. So the price that I pay for this loop here is that I need to carry one extra variable around all the way through. And that unfortunately makes the cost of inference much higher. So let's say each of those guys are binary variables, right? Then the separator set here between these two guys is 1 and 4. It's 1 and 6, 1 and 8, and so on and so on. And the trouble is that now I basically have a twice as large state as I would have had to carry through otherwise. Okay. Now there are some cases where you can just say, yeah, okay, let's just ignore it, right? And this is what people sometimes do in loopy belief propagations, especially if this chain is very long and you can really assume that anything that happened here didn't really affect the end very much. You can actually just do message passing in this loop. And in general, you can't guarantee very much. For the specific cases, you can actually, and there are some very nice results, and this would be a full class in graphical models, which show you under which cases things will converge or maybe approximately converge and so on. We're not going to go into this. Now let's just review the update equations again, because now we're going to do essentially, the generalized distributive law. So here was our update. So the message worked as follows. The message from B to C was given by, we go and sum over everything that's in B but not in C of f of x b times all the incoming messages that I received which now of course depend only on anything xb-like. So this might not really depend on all the variables in xb, but just some subset. And here, and then in the end get, p of xb, for instance, if I want to get this. It's going to be, whatever potential I had, just depend on xb, times the product of all the incoming messages. Okay. Any questions about that so far? Because that's as abstract as it's ever going to get in terms of graphical models. Yep.
Do these messages really depend on the intersection, or is it like B without A?
Well, so those messages, well, it's really only, well, I mean, a message coming from A to B cannot contain anything in terms of any coordinate that is in XB that wasn't in XA. Because XA cannot know about anything in XB that wasn't in XA. So therefore it's really the intersection. But I could have an incoming message from a different plate that actually contains some information that XA was never privy of. So therefore, the different messages may very well have a different domain of validity. This was not the case when we just had a simple tree. But now that we have a junction tree, this can actually happen. But that's really all you really need to worry about. Yep.
One thing that we addressed in 281A was the idea of marrying graphical models.
Yes.
Before you're doing this. You didn't mention any of that sort of stuff.
Okay, so I implicitly did that by just saying if I have, a function that depends on all these other variables. Yeah. So yes, what you would need to do is, if you have a child that depends on various parents, you would effectively get a clique potential that depends on the child and all the parents. Yes. Now, you can either do that explicitly, or you just look at the adjoint probability distribution and it falls out fairly immediately. So there's one paper that's actually very readable. It's called Factor Graphs, and it's by at least 3 authors, Xishang, Lulliger, and Frey. Yeah. I hope I didn't butcher his name. And it's called Factor Graphs. I would recommend that you read this paper rather than the generalized distributive law papers, simply because it's, I think, a lot more readable, as in easier reading. Secondly, the domain of application is slightly larger because the GDL papers essentially only talk about undirected graphs, whereas this talks about, directed graphs, and it falls out very naturally why you shouldn't really need to treat them very differently in terms of any inference procedure. Basically, you just have, a function which is given by a product of terms, and in the end you need to sum over some of them, and so, what remains is you just need to get rid of the others. So that's why factor graphs, I think, are a slightly more easily understood way of essentially discussing the same mathematics. So it's an IEEE information theory paper. Okay, I might get you a link for that when the slides are up online. Okay, now, here comes a typo. It's the generalized distributive law. And here's the key idea. So in dynamic programming, we really only used the fact that, we had those sums and multiplications. And we were able to, replace them with, and basically all we really use is the fact that, A plus B plus C equals A plus B plus C. And the second thing was that we were able to, you know, replace A times B plus C by AB plus AC. That's really all we did. We had, you know, products and so on. By the way, are there any questions? I'm happy to answer your questions. But you need to ask them first. Would you like to ask a question? Yeah.
Sure. What's the set you're in?
Okay. Very good question. And I'm going, that's exactly on the next slide. So, basically, for the purpose of this class, all you need to care about is that those two laws, namely the associativity and distributivity, apply and the operations are well defined. So in other words, you need to be able to define an equivalent of a sum and a product, and, well, you need to be able to operate with it. So the easiest way to actually then, you know, extend the algorithm that I showed you so far to anything else is to really just, you know, first replace, you know, plus and times by a plus with a circle, a times with a circle, and then afterwards, you know, substitute in whatever operation you would have picked. So the first example of a semiring is, you know, the plus and times semiring. Okay, that's easy, right? That's just what we started with. Here's another one. And this is the one how you would actually want to implement a lot of this stuff. It's the log plus and plus semiring. Make a table. Here we have plus, and here we have times. Well, of course, plus and times, that's fine. Now, what I'm going to do is I'm going to use the log plus operation. And that basically is as follows. It is log of e to the a plus e to the b. And times is going to be plus, so that's basically a plus b. And let's just recall the conditions that we need to show, namely that a plus b plus c equals a plus b plus c. And we need to show that a times b plus c equals a times b plus a times. So these are the two conditions we need to prove. So let's prove them for this. That's about the easiest thing that you can do, because if you squint at it, it's basically the original semiring and we've just taken logs of everything. So from that you can already see it's going to work, but I'm just going to walk you through anyway, because it's quite instructive if you've never done this. Who's done this before? Not some. Okay. So at least it's going to be useful for everybody. So let's do the. So what we have is we have basically the log of e to the a plus e to the b, and then we have that x plus e to the c, and the log again. Okay, right? So that's basically this term here. Now that's of course nothing else but, you know, we bracket. So x and log cancel each other out. So we have basically e to the a plus e to the b plus e to the c. And then of course I can go and insert an exponent log again. So I can write this as log of e to the a plus x log e to the b plus e to the c So the first condition holds. Right? So that's easy. Now let's show that the second condition holds, that A times B plus C is A times B plus A times C. So in this case, well, we have A plus, because that's basically the times operation. And now we have log of e to the b plus e to the c. Okay. Right. Now this I can immediately write, because I can push the a into the exponent as, you know, log of e to the a plus b plus e to the a plus c. We actually talked about that at some point in order to make sure that we don't have numerical underflows or overflows. Okay. So you can see these are equivalent. So that proves the second condition. So we know that log plus and plus is a semiring. Good. Now let's move on to a semiring that's a little bit less standard. At least you would have seen it in a very different context. And that's the, well, max and plus. So basically what we have here is max, we have n plus. So what I now need to show for the first condition is that the max of A and B, and then the max of this and C equals the max of A, and then here insert the max of B and C. But that's obvious, right? Because both operations will give me the maximum of all three, so therefore I have equality. Now the distributivity is going to be a little bit more fun. So what we get for distributivity is, you know, A times, so we have A plus the max of B and C. Right? And we claim that this is the same thing as the max of A plus B and A plus C. And, well, that makes perfect sense, right? Because the max, if I add something into the argument, is going to be the same thing. So the max plus is fine. You can check that the Boolean semiring does that. And you can also have, rather than the max, the min. You'll see that the min operation also goes through. And these are actually some of the more interesting semirings. One that could be quite interesting is, well, set union in intersection. And if you think about it, you can probably reduce it to the Boolean semiring. And I guess you will be thinking a lot more about it in your assignments. So I hope that helps you a little bit with finding a solution for the assignments. Okay. Now, where does this occur, right? I mean, after all, I mean, this at the moment just sounds like, you know, general abstract nonsense. Let's do some, you know, completely bizarre algebra. You know, why would I care about, you know, replacing plus in times, which is perfectly fine, by anything else? Well, I could, for instance, ask the question, you know, what is the most likely annotation of that chain? So I have a chain of events, and I could ask, what's the most likely chain of events that could occur? I might still be interested in, how likely is that most likely chain of events, but it's generally a reasonable question. So this is a reasonable question, for instance, if you try to recognize speech, right? Because the most likely chain of events of, what I had in my mind is the thing that I need to output in my speech recognizer. By the way, if you chat in the first few rows, it'll end up on video, and everybody will hear it on YouTube. So, you choose. So, okay, so let's go through this, because this is really the very same thing that we had before. So I want to find the most likely sequence through all those terms. Well, when do I get this? Well, these terms, for instance, occur in the shortest path setting, or also if I want to have, the maximum likelihood annotation. So let's just write down the joint probability again. So we had P of x was the product on P1 with x1 times then the product I going from 2 to n P of xi given xi minus 1. Now, if I want to find the argmax with respect to x of this expression here, what I can do is I can take the log of that. Now, this is max of the log of this. And now I get plus a sum going from I from 2 to m of the log of these expressions. So what just happened is that I turned the product into a sum. So, there you go. And that's exactly what I want to maximize. Okay. Now, if I want to maximize this, I can again do dynamic programming right from the start to the finish. So the first term here, let's call it L naught of x naught. That occurs only here and in S of x1 given x0.
There's a plus between?
What?
There's a plus between L naught and S on the next line?
Yeah, so this term here depends on x1 and x0, and then x2 and x1 and so on and so on. So basically I'm just collecting all the terms that depend on x0. So all the terms depending on x0, I can take the maximum over, because the only term that depends on x0 and something else is the one that depends on x1. So I get this least here. I can explicitly maximize this for a particular solution of x1. And then I can iterate and get a solution for x2. And I can just keep on going. So this is how I can find, in the end, the most, let's say most likely assignment for maybe x3. Okay. So now that I have the most likely assignment for x3, I can go back. And because once I know the best assignment for x3, I can figure out what the best one would have been for x2. And once I have that, I can figure out the best one for x1 and then x0. So I first do the forward pass to eliminate everything but the last guy. And then it's just like you're unzipping a zipper, you go really back from one node to the next. Of course, in practice, you don't throw those intermediate steps away. You basically keep a table around, which tells you, well, and this is sometimes called a trellis. It looks just like one. Let's say we have 3 states. So here's x0, x1, x2, x3, x4, x5, and so on. And we have 3 states. 0, 1, and 2. Now, what I'm going to do is I'm going to figure out, well, if x1 had a particular value, which x0 would I pick? I would pick this guy. If x1 had that value, maybe I would pick this guy as well. If it had that value, I will pick this. Now I go to the next step. Well, maybe I get this. Maybe this guy will go here. Maybe this one will go here. Maybe then I will, at the next stage, decide, well, I might go here. This one will go there. And the third one might cross over, and so on and so on. So the thing is, these guys always are connected at the higher level node, but not necessarily at the lower level. And then it just so happens that I ended up picking this last line, x5, maybe I pick state 1, and I can trace everything back. And that's basically what you then do in solving the dynamic program. You use the last guy to figure out the previous one, and so on and so on. Something cool actually happens here in between. Does somebody have an idea what happened at x3? So if you look at the chain, x3 special. Does somebody have an idea? Well, once I am at x3, all the paths will lead me to a well-defined state for x0. No matter which one I trace back, right? I could trace, this guy back. And yeah, okay, didn't work out, sorry. But in general, okay, sorry. Yeah. Here. The point is, after a long enough chain, those things will usually coagulate. And that's quite nice because it means that you don't necessarily have to do your full dynamic programming sequence up to the very end in order to figure out what would have happened in the beginning. You can already, sometimes guess the solution early. So that's nice for online dynamic programming, in particular if that part of the sequence is still actually being observed. Right. So if you don't actually know what the future is, you might still be able to find a consistent interpretation of the past. That's useful if you, for instance, want to track a plane. Well, given the current evidence that I've had so far, I know which plane has to be which one, even though I haven't really seen the future yet. The other case where this is really useful is what's called coupling from the past. There's a specific type of samplers which start with essentially all possibilities right now, and they end up narrowing things down and further and further. And if at some point all the paths lead to one common solution, you know that now you don't need to continue sampling any further because, well, it doesn't really matter what happened beyond that point. We're not going to go into this in detail. Probably a class on applied Bayesian inference techniques would be more appropriate to discuss that in a lot of detail. But that's essentially what you can do in some cases to come up with fairly interesting samplers. And the nice thing about those samplers is that you actually have a guarantee that your chain burned in, which usually in MCMC methods you don't have. So these are very beautiful methods if you are lucky to have a problem where it fits. Okay. So this is an example where we now can actually get that chain, work our way back, and it's essentially the same algorithm. So if you're not too scared about maxes and pluses, but actually treat them as pluses and times, you're in good shape. Yep.
So then, just to solidify the connection, are you saying that the choice of semi-ring operator that we use is essentially just the same set of algorithms, but if we just substitute out the different semi-ring, we'll get a different result?
Correct.
I see.
Correct. And as a matter of fact, what I did here is an Emacs query replace to get this slide from a previous slide that you saw. So it's that simple. and you can, for instance, just do operator overloading, and you replace one operator by another, and you get a different algorithm out of it.
So,
Yep.
so as a follow-up then, so I mean, you have a couple examples there, right? Like
Right.
log plus and that, right?
Yeah.
So is there a sort of an intuition, I mean, this kind of is the map estimate of it, but is there an intuition for like what some of these other operators might represent?
Yes.
Then applied to?
Yes, so for instance, what you would get for the set intersection and union semi-ring, you can use this to actually then sometimes on the fly build things like actually a junction tree. Because sometimes you just have, a sensor network and you don't actually know, who is really talking to whom. And then you need to establish on the fly what your actual graphical model is. And the only thing that you know is who your neighbors are, but you don't really know the full tree. And so you can actually establish those things on the fly and then run an inference procedure on top of that. There's some very nice work that Carlos Gestrin did about maybe 6-7 years ago on that very issue. It's actually very, very beautiful engineering. And there was a time when you could basically use those ideas, apply them to a field that had not been infected by semi-rings yet, and get best paper prizes. That time, unfortunately, is a long time gone. There is only a limited set of such semi-rings that work really well and that are popular, and I've pretty much shown you all the meaningful ones. It's basically, just plus times, max plus, set union and intersection. The Boolean semi-ring, which you can immediately see, is a special case of union and intersection. And then probability semi-ring is really just a different representation of what we already had for plus and times, but only restricted to non-negative numbers. And the tropical semi-ring is basically the same thing as what we had with max and plus, just now with a min. And these are essentially the important ones. I mean, you can have modulo semi-rings, and I think if you go into algebra, you'll probably encounter a few other bizarre beasts of that kind. But in terms of engineering applications, that's pretty much all that there is that really helps you. But for instance, it means that next time you look at the shortest path algorithm for path planning, you'll probably think of that very differently, because rather than that operation, you could replace it by a different semi-ring. It turns out that in some cases, some of those operations are easier to deal with than others. So it does not necessarily mean that all of those algorithms always have the very same complexity. In some cases, for instance, if I have a min or something like that, I can actually take computational shortcuts that don't work otherwise. But at least it means if you have a generic algorithm that is fast, it will apply to everything. Okay. And I think that's a good place to stop for right now, because we're going to apply this to junction trees after the break.